Hello everyone, my name is Yuta Yajima. Today, I'd like to talk about the refining similarity matrices through cluster attributed networks accurately. First of all, let me talk about an introduction to our field of network clustering. In this context, the network consists of relationships between objects such as users and papers. The networks represent various datasets that have become larger in recent years, such as SNS and the Google Scholar. Therefore, by clustering the network, we can understand some properties of various real-world big datasets. For example, by clustering a social network, detected clusters are considered to be communities. When companies use SNS to advertise their products, they can distribute advertisement to the communities that may be interested in their products. The task of the network clustering is divided into two main steps. First, based on the information of the network, objects in the networks are embedded into a vector space. Second, we cluster the objects in the vector space by using an algorithm, such as k-means. In the first step, the embedding is important because the embedding affects the accuracy of the clustering. In the second step, we introduce an existing embedding algorithm. When inputting a similarity matrix with similarities between the objects, spectral clustering (SC) embeds objects in a vector space so that objects with high similarity are placed closer one another. The similarity matrix S is said to be of high quality when the similarity between objects that belong to the same desirable cluster is high, and the similarity between objects that belong to different desirable clusters is low. Therefore, embedding and clustering using the similarity matrix works well if S is high quality. Therefore, this task, to derive a high-quality similarity matrix, is very important. Next, we introduce an existing algorithm called SClump to generate a high-quality similarity matrix. SClump clusters the network with two features, A sub S and L. A sub S is a single attribute of each object. For example of this network, each object has a single attribute of either businessman, review, or customer. L represents the relationship between objects. In the left example, customers post reviews. Objects is rated by reviews. There are two main characteristics of SClump. The first is to derive high-quality similarity matrices using meta paths. The second is that SClump defines a similarity matrix S generated by the meta path to achieve high accurate clustering of networks. The some following slides gives an overview of SClump, which is the base of our study. First, I'd like to talk about the first characteristic of SClump. SClump calculates the similarity between two objects using meta paths. A meta path is a path consisting of multiple relations. For example, the meta path 1 consists of two relationships, B2R and B2R, where B and R represent the businessman and a review, respectively. This metapath means that two businessmen with the same review. In addition, the metapath 2 means that two businessmen with the same customer. That is, metapaths can be used to find commonalities between objects, which is the reason why metapaths are used for a similarity measure. Specifically, the more metapaths between objects, the larger similarity between the objects. Next, I'd like to talk about the second characteristic of SClump. By using the metapath, SClump derives multiple similarity matrices. However, only a small subset of the metapath is useful for a clustering task. For example, we consider the case that the metapath 1 generates this high-quality matrix, while the metapath 2 generates this low-quality similarity matrix. In this case, we can cluster accurately by using the former matrix. However, because clustering is unsupervised learning, we do not know which matrix is high quality. In this scenario, the straightforward method is to compute the weighted sum of these matrices with this uniformed weight vector lambda, which results in this low quality S. However, if lambda is adjusted to assign large weights to high-quality similarity matrices, we can obtain high-quality similarity matrix. Therefore, learning relative importance of the metapaths increases similarity matrices quality. In addition, Nie stated that optimizing similarity matrix S so that S corresponding graph consists of connected components increases quality of the similarity matrix. This optimization is expected to detect the derived connected components as desirable clusters. Therefore, the refinement of the similarity matrix involves two variables, weights lambda for metapaths and the similarity matrix S. To achieve this refinement process, SClump solves this optimization problem with two variables, lambda and S. Then, SClump achieves the refinement to increase the quality of the similarity matrix and high accuracy clustering. In the previous slides, I told about an overview of SClump. So I'm going to explain the drawback of SClump and the motivation for our study. In recent years, clustering of attributed networks, ANs, which consists of multiple attributes AM and relationships L, has become popular. The refinement process proposed in SClump can be applicable to the networks in which each object has only a single attribute value, which is not true of our ANs, in which each object has multiple attribute values. And therefore, in our study, we extend the refinement process of SClump to achieve high accuracy clustering of ANs. Our proposed method is divided to two main processes, new similarity measure and partial refinement. Before explaining the new similarity measure, I'd like to explain the reason why the refinement of SClump cannot be directly applied to ANs. The refinement is to learn weight lambda for these multiple similarity matrices that are summarized in a similarity matrix S. SClump uses metapaths to generate these multiple similarity matrices. However, the metapaths cannot be used with ANs, whose each object has multiple attributes. Therefore, we propose another new similarity measure based on multiple LM and L in ANs, so that downstream refinement process and spectral clustering can be applicable to ANs. Next, I'd like to talk about second process, partial refinement. This second process is an extension of the refinement process of SClump. The refinement process of SClump optimizes S so that S's corresponding graph consists of connected components. However, the refinement process might create two small connected components, which consist of only outliers. Therefore, we extend the refinement process of SClump to new refinement algorithm so that sizes of connected components are almost the same. Now, I'd like to talk about the first process in some following slides in details. We propose a new measure based on AM and L to derive high-quality similarity matrices. Specifically, we calculate similarity matrix SA based on attribute AM and SL based on relationships L. First, I'm going to talk about how to derive similarity matrices SA. Each object OI in ANs has d-dimensional attribute vectors AI. Then we calculate similarity between ith object OI and jth object OJ by using Gaussian kernel. We derive d-similarity matrices SA1 to SAD from the d-dimensional attributed vectors AI. Next, I'm going to talk about how to derive similarity matrix SL. First, I discuss the concept of the similarity measure for SL. For networks shown in the left side, the directed relationships between the objects indicated by the blue solid arrows becomes a similarity. In addition, in this study, when OI can reach OJ by following some directed relationships, we add the new similarity between OI and OJ as a transitive relationship indicated by dotted blue line. We expect that this densification of similarities increases the quality of SL. The similarity between OI and OJ is calculated by the following similarity measure. I explain an overview of this similarity measure. The shorter S, that is, the shorter the transitive relationship between the objects, the greater the similarity. In addition, when S is fixed, the greater the number of transitive relationships from OI to OJ, the greater the similarity. The above measure is normalized depending on object i's degree. When object OI relates to too many other objects, the similarity between OI and OJ is decreased. After obtaining SA1 to SAD and SL, we compute the weighted sum of these matrices to derive S. Now that we have generated S to refine, I'm going to talk about the second process, partial refinement. First, I would like to provide additional explanation of the refinement process of SClump to clarify the difference between our partial refinement and the existing refinement. SClump solves this optimization problem using an iterative update approach. In each iteration, SClump updates one variable, whereas the remaining variables fixed. When the variable to be optimized converges, SClump finishes the iterative update. In this refinement process, two small connected components, which consist of only outliers, might be created. Then, we extend the refinement to make sizes of connected components be almost the same. To extend the refinement, we use the Charette score, which is a popular measure for the evaluation of clustering validity. For the following detected clusters, the more evenly sized clusters, the more separated clusters one another, the higher the Charette score. We aim to ensure that the graph corresponding a similarity matrix consists of connected components of equal size by the refinement process. Therefore, a partial refinement in our method stops the refinement process when this silhouette score reaches highest. The silhouette score silhouette I for each iteration I is calculated based on the clusters Ci. We obtain a set of clusters Ci by inputting Si into spectral clustering, where Si is updated I times using iterative update approach. Thus, this if statement is a convergence criteria for existing refinement, and this if statement is a stopping criteria for the new partial our refinement. We output the set of clusters when either of the two criteria satisfied, and we achieve the clustering of the AN. Now, I'd like to explain the experimental setting. This table shows the data sets consisting information on social networks and citation networks. To evaluate the clustering accuracy, we used these two popular metrics, Normalized Mutual Information (NMI) and Purity. The values of the two metrics ranges from 0 to 1, and the larger the value, the higher the clustering accuracy. We proposed a process that uses transitive relationships in addition to direct relationships. To verify the effect of the usage of transitive relationships, we changed parameter theta. When the theta is set to 1, only the direct relationships is used in our method. When the theta is 2 or more, the transitive relationships is also used. The NMI was the best for all the data sets when we set theta to 3. Therefore, these results demonstrate that using both direct and transitive relationships is effective for clustering ANs. The left figure shows the NMI of clustering datasets when using the refinement process. The horizontal axis of the figure shows I, the number of iterative updates of the refinement. The vertical axis shows an NMI when inputting Si updated I times to the spectral clustering. For the football datasets, the silhouette score reaches the local maximum when I is 2. Therefore, the NMI at I equal 2 was obtained by partial refinement, and the NMIs at the subsequent I were obtained by the existing refinement of SClump. This figure shows that the NMI obtained by the partial refinement is higher than the NMIs obtained by the refinement of SClump. This finding was confirmed in all the datasets. Furthermore, we compared a partially refined similarity matrix with a perfectly refined similarity matrix. Each diagonal block in the partially refined matrix indicates similarities in a connected components, similar to one of the supervised clusters. Compared to the perfectly refined similarity matrix below, the partially refined similarity matrix shows that each diagonal block is denser and sizes of all blocks is almost the same. Therefore, the partial refinement with the high silhouette score contributes to the detection of even and separated clusters. We also compared our method with 3 state-of-the-art clustering methods without using the refinement process: MVAP, CSNA, and SSB. The result shows that our method with the partial refinement of the similarity matrix is very effective for high accuracy clustering of ANs. This is a summary of this study. These are references. Thank you for your attention.